So now we want to go back to the spinning pointer. Where we have the pointer coming to rest at any angle between 0 and 2 pi, and we are, as I said, we are using the open interval 2 pi to indicate that 2 pi essentially is identical as 0, right. But the pointer, obviously there are no negative numbers as the outcome of the experiment. There are no numbers bigger than or equal to 2 pi as the output of the experiment. So the set of numbers we can get, the angles we can get are limited between 0 and 2 pi. Okay. Okay, so this only tells us this only tells us the sample space. Then of course then I am going to also let capital X of omega also be omega itself. Again, this is the simplest definition of the random variable x in this particular case, right. So okay, now the third before to proceed further to calculate the CDF of this x, we need to put a probability measure on omega. So how are we going to do it? Again, it turns out that the simplest probability measure is a so called uniform probability measure. Simplest P is defined is basically you take any interval a b whether open or closed, where these two numbers a and b are between 0 and 2 pi. So we say that we will make this probability assignment to this interval. This, it turns out now here we are actually assigning a probability directly based on the interval length, which is b minus a. We are not using the CDF as such. I mean, we are being more general than CDF. In the CDF we would go minus infinity to x naught, but I am doing it more generally now for two points a and b. Of course I am going to assume that for any a and b which is between 0 and 2 pi. So if I pick two angles between a and b between 0 and 2 pi, I am going to say that the probability of observing that the pointer is stopping in that interval is basically this b minus a divided by 2 pi. Why divide by 2 pi? Because it is a normalization. We want this probability to be between 0 and 1, or to have a maximum value of unity. When does it have a maximum value of unity? When you consider the entire dial, right. When you take b to be 2 pi, when you take a to be 0, then you are asking for the probability that it stops somewhere on the dial, which is obviously always unity. It has to stop somewhere on the dial, is not it? Okay. So it turns out that this p of ab is equal to b minus a by 2 pi only if this a and b are both real angles that you can observe. But when you talk about CDF, we have to now define the CDF for any real argument, and without getting into too much of explanation about this, let me just define the CDF for this particular random variable, identity random variable. So here it turns out that this fx of x basically can be defined like it is basically 0 for x smaller than 0. If x is negative or even 0, the CDF has a value 0, because this basically is saying that you cannot get any negative numbers to the output of the experiment, and any interval of the type minus infinity to x when x is negative has 0 probability. It is basically a null event or impossible event, right. Now if you take values of x between 0 and 2 pi, it becomes x divided by 2 pi for numbers between 0 and 2 pi, and in fact we can even put an equality here, because if you put x equal to 2 pi, it basically becomes 1. I can put less than equal to everywhere here because I am only defining this function, and it is actually continuous. So it is continuous everywhere, so therefore it is perfectly okay to write it with the less than equal to, although some people might leave out some of these equal to's in some ways, but it does not matter. I think it is better to for our understanding sake to appreciate that it is a continuous function. So, even though you are defining in as 3 different things, you are defining them to be 3 different pieces are all continuous. So, essentially it looks like a simple ramp. It goes like this. So, basically here you get impossible events, impossible or null. Why impossible or null? Because you can never observe negative angles. The angles you can observe are always between 0 and 2 pi. Now, once you once you observe an angle, I mean once you say, well, I pick a number x which is this x is entirely under your control, you can ask for the probable CDF of 0.5 or say CDF of 1 or the CDF of whatever between for any real number, any real argument x. So, remember that the CDF of any random variable is specified to be defined for all real numbers, not irrespective of the omega. Okay. So, this it's impossible or null here, and here when your argument is between 0 and 2 pi, if fx increases linearly, the CDF increases linearly because you are assigning probabilities in this fashion. If you do not assign probabilities like this, then it is not going to be this linear increase. Now, why are we assigning probabilities like this? Because we are saying that the probability of an interval is proportional to the length of that interval, right. So, if you take a longer portion of the dial, it has that proportionally higher probability. The entire dial has probability unity. A small portion of the dial will have a smaller probability, which is scaled down by the length of the or the interval of angles that you specify out here. So, if I specify pi by 2 to 0, then it will be 1/4, or if I specify pi by 6 to 0, it will be pi by 12 or 1 by 12, sorry, or if I specify pi by 3 to pi by 2, it will be whatever. So, this assignment of probability is just our way of recognizing the fact that the pointer stops uniformly on the dial and does not favor any particular interval over any other interval. So, all intervals of the same length are identical as far as the pointer is concerned, which is what we expect in practice, unless we have a funny a spinning mechanism which is not which is deliberately or whatever, for whatever reason not uniform. But anyway, that is a very much more complicated situation. So, we take the simplest case again, which is a nicely well oiled machinery, which means that the pointer stops at any point regardless of where the point is on the dial. Okay, so we have an impossible or null event for small x between 0 minus infinity and 0, then we have this linear increase, and then we have once the CDF hits unity, then it stays at unity, it cannot increase any further. So, and what does this unity mean? This now becomes a certain event. In other words, it is certain that you will observe a real the pointer value will be between minus infinity and 10. For example, if this number is 10 or 9, because 2 pi, as you all know, is 6.28 or whatever it is, and therefore any number bigger than that means the probability of the interval from minus infinity to up to that is always unity. So, it becomes a certain event once you go beyond 2 pi, and an impossible event if the upper limit, this x here, is below 0. So, this is a very simple example of a CDF assigned to this identity mapping, but in general this calculation is not, again I have to warn you, it is not an easy calculation to do, and you cannot very easily extrapolate from this. You cannot claim that in general it is always going to be an easy thing to do. In general it is not, and I think it is better that we do not consider more complicated examples right now, because it would not really serve in much of a purpose. That is what so we will see how far we can push this, right. and most of the things that we will do in the immediate, for the immediate few next lectures is basically to consider this situation. We take some portion of the real line, not necessarily 0 to pi, it could be any 0 to infinity, for example omega could be any non-negative real number, and we define x omega to be omega. So then we can immediately we don't have to worry about bigger spaces or anything of the sort, right, and calculations become a lot simpler. So the last thing that we need to clarify is now the density, the PDF, right, of a continuous random variable. So PDF, the density function, probability density function of a continuous random variable is basically fx of x. Once you find the CDF, you can, and the CDF is continuous, you just define it for differentiate it for all, through everywhere the real line, and then you get by differentiation you can go from the CDF to the PDF, which is exactly what we did earlier. So in other words, this is going to become the uniform PDF between 0 and 2 pi. So this is going to be capital F, this is going to be the density function, and to obtain probabilities of intervals as we did earlier, we have to integrate this PDF over A to B or whatever, right. So it becomes in this particular case it is very easy to go back and forth between the PDF and the CDF. So all that we require to obtain this PDF is just that basically we are not even bothered so much about these corner points, where as long as the CDF is continuous and as long as these points are few in number, we can always differentiate this to get this. Let us not worry about the exact value of derivative here and here. We can define them in some consistent way, that is the exact value of derivative at 0 and 2 pi is not of any importance at all. Okay. So therefore for a simple case we have looked at how going from a given probability assignment we can calculate the CDF and then get to the PDF by differentiation. In many examples that we are going to look at, we are going to start from the PDF, right. We are going to say let x have this PDF density function to a small PDF, right. Oh yeah, of course thankfully P and C are different, right. So PDF, so we are going to start with some PDF and then say what can we do with it. Of course we can always obtain this CDF by integration going in this direction. That is again as we did earlier. The only difference between the earlier lecture and now is that we have attached the name of the random variable to a CDF or PDF. And how are we doing it? We are saying that the CDF of any random variable is basically the probability that the capital X takes values between or no bigger than the argument. So I mean let me not, I have said that enough, so I am not going to write it. I am just going to define the domain of fx. So fx is basically a function which takes you from r to 0 to infinity as always, right. So again by domain extension or it depends on how you view this, you are defining the entire, you are defining the CDF or PDF, sorry, the PDF over the entire real line from minus infinity to infinity. It could be 0 over most portions of the real line. Wherever it is non-zero, in this particular case between 0 and 2 pi, that interval of the real line is called the support of the PDF. So basically it is that the PDF tends to, in many cases, in many examples tends to be non-zero only over a support interval of the real line. The rest of the real line it typically takes the value 0. So that means that the random variable takes values only wherever the PDF is non-zero. But again as I said earlier, the value of the PDF is not a probability. The value of the PDF is never a probability, right. Only by integrating the PDF do you get actual probabilities. Then I said earlier also that the concept of CDF is more general than PDF. All random variables basically they have CDFs, whether right continuous or discrete. or any random variable basically has a CDF. So that means that CDF now turns out to be the mathematically unifying concept of for a random variable, whether it is continuous or discrete, right. So what kind of a CDF does a discrete random variable have? Turns out that discrete random variables have staircase CDFs. Why staircase? Because so let us say these are the values that the random variable takes, x1, x2 for example, just let us say let it only take 2 values. In other words, it goes from 0 to the random variable takes only values only 2 values, right, like head or tail 0 1 whatever, right. So up to x1 you have a null event, and so the probability of the random variable x take of taking any values in an interval is 0. If you include x1, then it jumps, the CDF jumps to some value between 0 and 1, and then at x2, because now it becomes a certain event that the random variable will always take values between minus infinity and x2 included, at x2 the CDF jumps to 1. So the CDF ends up being right continuous and a staircase, which is actually quite messy to specify analytically. That is why for discrete random variables we typically do not specify their probabilistic behavior in terms of their CDF, because this type of function is very messy to write down. Okay, I think we have said enough things today. So one last point again, I mean before closing is that just because you have a continuous space, you need not necessarily always define a continuous random variable. You can also define a discrete random variable by the process of quantization. Let me just end this lecture with the example of how to define a discrete random variable on a continuous space. So if I go back to the spinning pointer, and if I do not define x of omega equal to omega, in other words I define, so omega, capital Omega is still 0 to 2 pi, but I define x of omega in this fashion. I define it to be 0 when let us say omega takes values between 0 and less strictly smaller than pi by 2. Now here note I cannot put less than equal to, okay. Then I say that the measurement takes the value pi by 2 for this range of output angles. So if this pointer is going to stop at any number between 0 and pi by 2 not included, I am going to say that the value of the random variable is 0. Then I am going to take, so I am going to extend this. So clearly I have to specify the entire range here, the entire omega here. So I have to, let me say I continue this in this fashion, pi less than equal to omega less than let us say 3 pi by 2 and then 3 pi by 2 for 3 pi by 2 to 2 pi. So this is now a full specification of a random variable, because I have defined an x of omega for all omega that can come out of the experiment. So this is exactly something which fits our definition of what a random variable should do, right. It should take some real value based on the output of the experiment. So that is what it's doing here. But omega x in this case is just the set of 4 values 0, pi by 2, pi, 3 pi by 2, which is certainly a countable set, and therefore x is, in this case x is discrete, it is not continuous. And you can talk here in terms of the PMF of this x. What is the probability that x takes the value 0? That is the probability that you observe this interval. What is the probability that x takes the value pi by 2? That corresponds to the probability of this interval, and so on. So you need not necessarily define, right, only define continuous random variables on uncountable omega, right, or when omega is a portion of the real line. You could define something like this, and then based on the probability measure you want to give to these intervals, that will induce the probability mass function, and induce the specific in individual probabilities of these points. So, I think I hope that with this the the idea of continuous random variable is clear, and we have covered we have understood how to marry the idea of CDF with and PDF of a random variable. We are not talking about them in some generic sense, but we are talking about them in conjunction with a random variable. And remember that the key point from that I said earlier, which is erased now, that the CDF of a random variable is a probability, and it basically equals the probability that random variable takes values which is no bigger than the argument that you give. So, the argument of the CDF or PDF is entirely deterministic. There is nothing random about the argument, that is entirely specified by the user. Okay, thank you.